Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at how to add and subtract vectors, both algebraically and graphically. By the end of this lesson, we should be able to add and subtract vectors algebraically and add vectors end-to-end with the parallelogram rule. Alright, let's go ahead and get started. So, in order to add vectors algebraically, your vectors must be in component form. Then, to add vector u, which would be x1, y1, and v, x2, y2, simply add the corresponding components. We call the result of the sum of the vectors the resultant vector, okay? Or, in a notation, vector u plus vector v would equal x1 plus x2, y1 plus y2. Here's our horizontal component, here's our vertical component. Let's look at this process through an example. So, we have vector CD, or we want to find the sum of vectors CD and XY, given that the points C is 0, 2, D is negative 3, 7, X is 3, negative 4, and point Y is 7, 0. So let's go ahead and find the vectors in component form. Vector C would be, or vector CD rather, remember that we have to do terminal point minus initial. C is the initial point, D is the terminal point. So vector CD would be x2 minus x1, comma y2 minus y1. We're talking about with the points C and D respectively. So this would be equal to, well, x2, that would be negative 3 minus 0, comma, y2 minus y1, that'd be 7 minus 2. And this would give us the vector negative 3, comma 5. Okay, so this is the vector CD in component form. Now let's find vector xy in component form. So x2 minus x1, this would be 7 minus 3. Again, because point x is the initial point y is the terminal point for vector xy. Then we have y2 minus y1, that'd be 0 minus negative 4. Don't forget your double negative there. And this would give us the vector 4, 4. Okay. So what we've done is we have found our vectors in component form for vector CD and vector XY, given the initial points and the terminal points. Next, we're going to go ahead and add the vector CD and XY together. So what we're going to do is we would say vector CD plus vector XY would be x1 plus x2, comma, y1 plus y2. So we're taking the vectors that we have, we're going to add their x values together. That would be negative 3 plus 4. And then the y1 plus y2 would be 5 plus 4. And this would give us 1, 9, the vector 1, 9. So this is our resultant vector, 1, 9, for vector CD plus vector XY. Go ahead and pause the video here, try the next example, unpause, and see if you got the problem correct. All right, so here's our next example. It turns out the answer is the same. We get the resultant vector is 1, 9. The points are slightly different, but the math works out the same. So go ahead and pause the video, check your work, and we'll move on to the next example. All right, so now that we've seen how to add vectors algebraically, let's look at how we can add vectors graphically. And the first method that we're going to talk about is the head-to-tail method. In this method, essentially, the tail of the second vector is placed at the head of the first vector, the tail of the third vector is placed at the head of the second vector, and so on if we're adding more than 2 or 3 vectors. Let's see those examples that we did algebraically and see if we get the same result graphically. So, looking here at our first example where we did vector CD plus vector XY given the points CD, X, and Y from that first example, what I've already done is I've graphed the points. So here's vector CD, initial point 0, 2, terminal point negative 3, 7, and then here's vector XY, initial point negative 3, 4, terminal point 7, 0. So notice all I'm going to do here is I'm going to take the first vector, I'm going to move the first vector over so that the tail of the first vector right here is matching up with the head of this vector. That's why it's called the head-to-tail method. The vector here, tail matching with the head of the other vector. Now, if I look from the tail of the first vector up to the head of this vector, basically go from tail to head here, we have the resultant vector, which we can see right here in red. And the resultant vector, if we count, let's look at the horizontal and vertical components. Well, the horizontal component, it just goes right 1 and then up 9. So the resultant vector would be 1, 9. Okay? And that should match exactly what we got algebraically. If we look over at our first example, algebraically, we got the vector 1, 9. So it does match. Let's look at the direction real quick. We know that the direction of a vector is the horizontal component or the vertical component rather, divided by the horizontal component. So the direction would be 9 over 1, which is just 9. And then looking at the magnitude, we have the square root of 1 squared plus 9 squared, and this would give us the square root of 82, which cannot be simplified any further. Okay? Go ahead and try the next example. So the next example is the same vector from example 2 with the algebraic method. See if you can graph the vectors, rearrange them with the head to tail method, and find the resultant vector. I'm going to go ahead and pause the video and try that, and then we'll go over the answer. All right, so here's that second example we did algebraically. Here's the vector CD. We have the point 1, 3. We have the point negative 2, 8. Here's vector XY. Initial point 4, negative 3. Terminal point 8, 1. Again, I'm taking this vector. I'm taking the other vector. I'm going to move the tail from this vector over to the head of this vector. And then I'm going to draw the resultant vector, again, from tail to head. And that gives us here this vector in red. Again, we can count the horizontal and vertical components. The vertical component would go right 1, so we have a positive 1. The horizontal, right 1. The vertical component would again go up 9, so we have 9 right here. The direction, 9 over 1 to give us 9. And the magnitude, once again, 1 squared plus 9 squared. That'd be the square root of 82. All right, so now let's try subtracting vectors. And essentially, subtracting vectors is the same process as adding vectors, but you have one extra thing to worry about, which is the negative. So when you subtract vectors, for example here, when you do CD, vector CD, minus vector XY, subtraction is the same as addition, but you're adding a negative vector. So this would be the same as vector CD plus the negative vector XY. So let's see algebraically what this turns out to be. So we've already worked with these vectors. We know that vector CD is negative 3, 5. This is from our first example. We know vector XY is 4, 4. And if I take the negative and distribute it to vector XY, I would get negative 4, negative 4. So again, I'm just taking this negative here, distributing it to the components of vector XY. We get negative 4, negative 4. So again, vector CD minus vector XY is going to be the same as vector CD plus negative vector XY. And that would turn out to be, let's see, we're going to add our x components together. So it'd be negative 3 plus negative 4. Then we would have 5 plus negative 4, which would give us negative 7, positive 1. So this is the resultant vector of vector CD minus vector XY. Now let's try that graphically as well. So once again, I've gone ahead and graphed them just to save us a little bit of time. Here is vector CD, initial point 0, 3, terminal point negative 3, 7. Here's vector XY, initial point 3, negative 4, terminal point 7, 0. And what we do is when you go from vector XY to negative vector XY, all that happens is the direction changes. So instead of the direction moving in this way, our direction now changes in the exact opposite way. However, vector CD remained unchanged. And now we're going to do the same exact thing as we did previously. We're going to take this vector, I'm going to bring the tail of the vector to the head of this vector, which you can see right here in this example. Go ahead and move that vector down, and the resultant vector is going to be from the tail of one vector to the head of the other. And if we count that, notice horizontally, because we're moving in this direction to the left, we're counting -7. Let's get right here, be consistent. Counting -7, but then we're going up 1, which is a positive direction, +1. Okay, so our resultant vector is -7, 1, which is exactly what we got when we subtracted the vectors algebraically. The direction, we can see the direction is 1 over -7, which is just -1/7 for our direction. And the magnitude, let's go ahead and we have -7 squared plus 1 squared, which is square root of 50. Square root of 50, we know that's square root of 25 times 2. And we know the square root of 25 is 5. So the magnitude is 5 square root of 2. All right. So that's how we can approach adding and subtracting vectors graphically. We also have a method called the parallelogram rule for geometrically finding the sum of two vectors. Essentially, if two vectors share a common initial point or can be drawn so that they share a common initial point, then we can form a parallelogram. It turns out the diagonal of the parallelogram going through the shared initial point is the resultant sum of the vectors. So let's try one out here, and then we're going to verify algebraically to make sure that it worked. So in this example, we have vector m, which is 2, 5. Let's go ahead and draw vector m. So vector m is 2, 5, has a 2 for the horizontal component, 5 for the vertical component. So notice I'm just going to draw it like this. Okay, there's vector m. Vector n is 6, 1, has a horizontal component of 6, vertical component of 1. And notice that I'm intentionally making the initial point a shared point. I'm making it at the origin. So what I can do now is I can complete a parallelogram using these same vectors. So to vector n, I'm going to take vector m and just move it over here. So this is what it would look like. Notice that vector m, again, had a horizontal component of 2 and a vertical component of 5. So I'm going to go over 2, up 5, which is right there. Let's get shape recognition on. And then same deal, I can take vector n, which had a horizontal component of 6 and a vertical component of 1. Do the same thing here. Horizontal over 6, up 1. And what ends up happening is the resultant vector is the diagonal going through the initial point. So that vector in red that I've drawn is our resultant vector. And we can go ahead and count to find the horizontal component and the vertical component. Horizontally, we're going from 0 to 8. So our horizontal component should be 8. The vertical component, once you've gone from 0 to 8, you go up 6. So the vertical component is 6. Now let's check algebraically to make sure that that's consistent with that's the answer that we should be getting. So if I add vectors m and n together, again, I'm going to add their x components, their horizontal components. Well, that'd be 2 plus 6. And then I'm going to add their y components, 5 plus 1. That'd be right there. Add them together. 2 plus 6 is 8. 5 plus 1 is 6. And notice that we get the exact same answer, both algebraically and geometrically. One last thing we want to talk about here in today's video is a special note about magnitude. So in general, it'd be tempting to say that the magnitude of the sum of two vectors is equal to the sum of the magnitudes, but it actually doesn't work out that way. And here's an example. Here's an example of why it doesn't work out. So let's have u be the vector 2, 5, and v be the vector -3, 2. Let's go ahead and calculate the sum of the vectors, u plus 5, or sorry, u plus 5, u plus v. And so u plus v, that would be 2 plus -3, and then 5 plus 2. Well, 2 plus negative 3, that's negative 1. 5 plus 2 is 7, so we get the vector negative 1, 7. Now let's go ahead and calculate the sum of the magnitudes. So we'll calculate the magnitudes for the two vectors individually, and then we'll add the magnitudes together. So the magnitude of vector u would be square root of 2 squared plus 5 squared. The magnitude of vector v would be the square root of negative 3 squared plus 2 squared. Notice I'm putting the negative in parentheses, good habit to get into. Square root of 2 squared plus 5 squared, well, 2 squared is 4, 5 squared is 25, so this is the square root of 29. Negative 3 squared would be positive 9, 4 squared is 4, 9 plus 4 is 13. So you get the square root of 29 plus the square root of 13. I can't simplify any further because neither of those will simplify, and they're different. They have different radicands, so we can't add them together. So that'd be the simplest form for that sum. Now let's look at the magnitude of the sums. So we've already done the sum of vector u plus vector v. That was negative 1, 7 right here. So now let's find the magnitude of negative 1, 7. This would be square root negative 1 squared plus 7 squared. Well, we know negative 1 squared is 1, 7 squared is 49. This is the square root of 50. And we know that 50 is 25 times 2, so this is simply 5 square root of 2. And we can see right here, the sum of the magnitudes in this example, which was square root of 29 plus square root of 13, was not equal to the magnitude of the sum of the vectors, which was 5 square root of 2. So while it may be tempting to say that, in general, the sum of the magnitudes, or the magnitude of the sum, is not equal to the sum of the magnitudes.